Okay, chapter 7 on linear transformations. So in this chapter we are looking at how matrices are used to transform points on 2D plane or three-dimensional space. And we are going to be talking specifically about linear transformations. So you need to understand what a linear transformation is. So in terms of matrices, you are going to have a matrix in 2 dimensions, A, B, C, D. And if you are trying to find the image of a point with the coordinates x, y, then you just need to multiply matrix by that point, and the answer you're going to get will correspond to its image. So in general, if you just put a general point xy, then you will have your image of the x coordinate. So x coordinate will go to ax plus by, and the y coordinate, so its image is going to be y dash, will go to cx plus dy. Okay, for the linear transformation, you need to obtain linear combination of x and y as your answer, as your image of those coordinates. What are the properties of the transformation? So geometrically, the origin is mapped to itself. So the origin will stay put, will not be transformed anywhere else. So a translation is not going to be classed as a linear transformation, because if you translate a point, it will go to which is attached at the origin, it will go somewhere else. It can be represented by a matrix with 4 entries, so it's a square matrix, and to get the transformed image you multiply its matrix by the position vector of the given point. So the common linear transformations that you know are reflections. It has to be a reflection in a line that goes through the origin, otherwise the origin will be moved somewhere else. Rotations, again, rotation needs to be done around the origin. And there would be also enlargements or scaling, so like enlargement along x-axis and enlargement along y-axis. So we'll have a look at the first example. So let's just see if we can answer this question. We're going to use this idea of finding the image of the point with the coordinates 2, 3. So here is my transformation. So it's not given in a proper like 2 by 2 matrix form. It might not be possible because it might not be linear. So let's have a look at the simply over here we are given that 2 can be substituted for x, 3 can be substituted for y. So this will go to 2 plus 4 and then 3 minus 1. So the image is going to be 6, 2. Okay, transformation T, you've got a linear combination of x and y, so it might be a linear transformation, but we are interested in finding the image of point 2, 3. So instead of x goes 2, so this is going to be 2 times 2 minus 3. Instead of x goes 2, and then instead of y plus 3. Okay, so that will go to 4 minus 3, so it's going to be 1, and 2 plus 3, which is 5. By the way, I've given the answer as a vector, so really should write it as a point. Okay, and finally you've got this one, so if you put 2, 3, simply substitute 2 instead of x and 3 instead of y. So this will go to 2 times 3, and this will go to minus 2 squared. So the answer is 6 and minus 4. Okay, in example 2, we've got to find the transformation matrices of the following mapping. This is like a mapping, but by the way, if I haven't mentioned it, this means maps to. So point xy maps to its image. So this is the point and that's the image. Okay, so over here, in order to find what the transformation matrix will result in obtaining this image, what you want to do is rewrite this as x plus 2y, so put them in order of alphabetical order, and this is 3x plus 0y. So the matrix is going to be 1, because you take the coefficient of x as 1, 2, that's the coefficient of y as 2, 3 on the bottom, and 0. Just to check, we can multiply 1, 3, 2, 0 by x, y. So if you do it, you're going to get x plus 2y and then 3x plus 0y. And this is what we had to begin with, except we had 2y written first, just to try and make it a little bit more difficult. There you go. Okay, so do the same tactics here. Xy is mapped to minus 2y, 3x plus y. So if you put them in order, you will have no x's, so 0x's minus 2y, 3x plus 1y. So the matrix I'll get is 0, minus 2, 3, and 1. Okay, so you had a linear combination of x and y, so this represents a linear transformation. Okay, you can obviously check the same way we've checked the first example. Okay, so let's look at example 3. So we've got a square with the coordinates 1, 1, 3, 1, 3, 3, 1, 3, so we'll call it square S. We're going to find the image of that square S. We're going to call that image S dash under the transformation that is represented by this matrix M. So what they're asking us is to find the images of the points, and you do it by multiplying the matrix by the point. So for part A, going to do minus 1, 2, 2, 1, multiply it by 1, 1. That will give me the image of point with 1, 1. So you got 1 times minus 1, so it's minus 1 plus 2 times 1, so plus 2, 2 times 1, which is 2 plus 1. So that will go to 1, 3. Okay, you do the same for the second point. Minus 1, 2, 2, 1, multiply it by 3, 1. So you're going to get minus 3 plus 2, so it's minus 1, 6 plus 1, which is 7. And then the next one, minus 1, 2, 2, 1, that can be multiplied by 3, 3. So you're going to get minus 3 plus 6, which is 3, and then 6 plus 3, which is 9. And then finally minus 1, 2, 3, 3, 1, 3. So you're going to get minus 1 plus 9, which is 8, 2 plus 9, which is 11. Before I do part B, okay, so you've got those 4 points. Let's write them down. 1, 3, minus 1, 7, 3, 9, and 8, 11. If you want to save a little bit of space or time, here's how to do it a little bit quicker. What you may want to do when you multiply that matrix by each point, you could say this is point 1. You could do it all in one go. That's going to be point 2. That's point 3. Let's actually call it A, B, C, and then D is going to be 1, 3. So if I call that one A, and that's B, that's C, and that's D. What I'm going to do, if I do all multiplication in one go, the first column will go with the image of point A, so we'll call it A dash. So look, you've got 1, 1 matching with minus 1, 2, so you've got minus 1 plus 2, which is 1, 3. That would have been our point A dash. Then you carry on and you do minus 3 plus 2, which is minus 1, 7. The next one is going to be 3, 9, and the 8, 11. As long as you don't get muddled up and you understand that each column of the resulting matrix represents a point, and then transfer it into coordinates of the point. If they ask you for the position vector of each point, you would have to take them out of there and write them as separately as above. Okay, so let's take those points, plot them. So you're going to get first point is 1, 3. So a 1 across, 3 up. So this is A dash, coincides with our point D. Then you've got minus 1, 7. So it's 1, 2, 3, 4, 5, 6, 7. That would be B dash. Then you've got 3, 9. So that's going to go over here. Okay, so the next point is going to be our point D, which is 8 across, 11 up. That won't make as much sense. Have I done 11? Okay, let me just double check. That was... Okay, I do apologize. I've copied this matrix incorrectly. That's why the last point is incorrect. Oh, I don't know what I've done here. Okay, so it's 1 times minus 1. It's minus 1 and then plus 6. So that will give me, let me just cross it, 5. And then you've got 2 and then 3, which is 5 again. So this point here is 5, 5. It's actually good to make mistakes because then you can check your answers. Go back when they don't make sense. Okay, so it's 1, 2, 3, 4, 5 across and 5 up. So that is D dash, and that makes sense because I was looking for something that looked like this. There you go. Okay.